Hi class, this will be the second video in the analytical discussion series, and so this week we looked a lot at equilibrium, and so I'd like to first off go over a problem of these in more detail, different to the ones that we've been doing in class using the ICE technique, and this one is taken from your homework assignment. So 6-25 asks you to calculate the concentration of a bunch of different zinc species in a solution that's saturated with solid zinc hydroxide. And the important point here is that it's at a fixed hydroxide concentration, as would typically occur if, say, you just add a set amount of base. So Harris's solution to this, I think, unfortunately is lacking in a lot of details on how he gets to the final solution. So that's why I'd really like to go through this one, as well as point out some discrepancies between what way you might solve it and the way that he did. Okay, so to start out the problem, always first write out all the chemical equations. These are what's going to give you what you'll use for the equilibrium expressions. So for each of these species here, we want to write out the equilibrium. The KSP is easy. That would just be the solid dissolving into the constituent ions. For the betas shown here, remember that beta always means complex ion creation. So in this case, it's just the ones with hydroxide, but it could be any complex ion, say with a bromide or any other ligand like that. So you write all those out, keeping in mind that it's not sequential addition. Like, for instance, it's not that the second one would be ZnOH plus 1OH. No, it's always for all of the hydroxides that are being added. Okay, so then from those chemical equations, then you can write the equilibrium expressions quite easily by doing just products over reactants. And so that's all shown here with the powers included. And keep in mind that in the KSP expression, the solid's not included because its reference state is itself. So that's just going to have two terms there. Okay, so then the next step is you want to look at these equilibrium expressions that you have. You want to pin it down to something that you know, something you can absolutely solve for. So in this instance, we know the concentration of OH, so look through all 5 of these equilibrium expressions and see which term only has one other term aside from OH, because we know the values of all our equilibrium constants. And so if we look at all of them, the one that stands out is the KSP, because you can see there that we can simply solve for zinc. So the next step is to do that, solve for zinc, recognizing that it appears in all the other equilibrium expressions, so that means that we can cancel it out. We solve for that, get KSP over OH squared, and then first write out all the species that we're looking for. So those will be all the various hydroxide complexes, first in terms of just how they appear in our equilibrium expression. So in the first one where we have B1 multiplied by the concentration of Zn by the concentration of hydroxide. Okay, so then once we have that, then we just plug in the values of Zn that we got before, and then it simplifies to a much easier expression that we have all the values for. So note that in the third equation here, you can simply get beta 2 times KSP. You have all the information for that. Harris does an odd substitution where he puts in beta 3 times KSP multiplied by hydroxide. Both are strictly true, but I think that just doing beta 2 times KSP is a lot more intuitive. Okay, so once you've gotten to this point, then it's simple. You just plug in the values and go from there. And so if you follow this systematic treatment each time, you can't mess up the equilibrium constants, which is going to help you out a lot. Any of you that have watched Breaking Bad almost certainly know the famous HF scene from the second episode of the first season. Walt and Jesse need to get rid of a body. And Walt, being the chemistry genius, knows that they can dissolve it in the highly corrosive HF. He sets Jesse to do it because he doesn't really want to get his hands dirty, but he gives him very specific instructions that he has to get a polyethylene container.
What kind of plastic, man?
Polyethylene.
I don't know, man. This feels kind of flimsy. Any decent acid's gonna eat right through this.
Not hydrofluoric.
Why not?
But he doesn't tell him why. And Jesse searches all over, can't find the one that he wants, And so he just decides to take matters into his own hands.
I barely got him in the bathtub.
Bathtub? What do you mean, bathtub?
Yikes. So what happened? Why did this work? Well, we've already learned in class that HF is a weak acid. So if it's a weak acid, why is it so corrosive towards things? So we went over the reason for that being that it forms ion pairs in solution because fluorine is so electronegative. Well, so its HF is a weak acid, but the fluorine that's formed is extremely reactive. So the two materials, the one on top that Jesse should have chosen, polyethylene, you can see is a completely saturated hydrocarbon polymer. So there's no real opportunity for this fluorine, despite being extremely reactive, to react with it. Now compare that to glass, or this would also apply to the ceramics that his tub was made out of. The HF can react with the metal to form these metal fluorides, liberating water in the process. I want to go into a bit on why it is so dangerous. And we can see that it solely is a matter of a few equilibrium expressions. So in the first one, we just have dissociation into the fluoride anion, but we know that that's going to form ion pairs in solution, and this is why it's not going to dissociate. It's not going to have a very low pH, but that doesn't mean it's not dangerous. So look at the last expression. This is simply the KSP expression for calcium fluoride. And we can see from the KSP in the tables that the value is very low. Okay, why do we care about this? Well, in your body, there's a whole lot of calcium. And HF is particularly bad about getting into your body because the ion pair itself is neutral. It can slip between your skin much more easily than simply ions can. So if we flip this equation backwards, then what we have is the reaction of free calcium, like is in your body, reacting with fluoride. And because the KSP was so low, that means that the equilibrium constant for the formation of calcium fluoride is going to be extremely high. And we can see we have a factor of 10 to the 10th. And so what this means is that this extremely favorable reaction is going to consume the calcium that's available right there in your body. Furthermore, that the depletion of F is going to push that second reaction to the left, so we form even more free fluoride from those ion pairs. And as more fluoride's created, it's immediately going to react with the calcium, and so HF, when it gets into you, will actually completely deplete your calcium supplies and can lead to death.